Hidden in the black magic of an oil reservoir is a climate demon from the distant past. And we unleash it at our peril.
What we know for sure is that we're doing something which will have consequences that we don't like. How bad those consequences will be, we can't quite tell.
Once you extract the oil and you start burning the oil, obviously you're displacing the equilibrium and you're pushing carbon dioxide back into the atmosphere, which we've been doing since the Industrial Revolution, I suppose, and forcing the Earth towards a new greenhouse future.
We would go back to a world that is weirdly going to be quite similar to the world in which the oil formed in terms of temperature, state of the oceans, and so forth. So there is a certain irony in this whole story.
To see our road to the future more clearly, we must first return to the past. We're heading back to the Jurassic, back to the steamy world of the dinosaurs, back to when the sand was sea. It was here, in the 100 million year interval between the early Jurassic and the mid-Cretaceous, that the vast majority of the world's oil was formed. But what was so special about this time? We know that the key to creating an oil deposit is for masses of organic rich plankton to fall onto a stagnant seafloor. This is how you end up with the stinky black mud that becomes the petroleum source rock. Simple enough, but this went only partway to explaining the huge size of the deposits that the geologists were finding. There was a puzzle here, and a link, it seemed, to some sort of global calamity. The first clue lay hidden in the Apennine Hills of central Italy. From the days of the very first dinosaur to the last, this whole rocky landscape was mud at the bottom of the sea. In the early 1890s, a wandering geologist noticed a discrete band of black organic rich shale, sandwiched between the otherwise normal limestone.
This 1 metre of black shale was little more than a curiosity, and it might have remained just that were it not for one very important factor, and that is the discovery in the Pacific Ocean in the early 1970s of black shales just like this one, of identical age. So all at once, people began to realize that this was not a local phenomenon, but it was a global phenomenon.
It was a revelation. Up until this point, geologists had explained oil source rocks only in terms of specific local conditions, say a particularly fertile stretch of coastline or a naturally stagnant patch of sea floor. But here was evidence of something much bigger going on. Something big enough to suck the oxygen from oceans right around the planet. It's now thought that the world's richest source rocks and the most prolific oil regions are largely the result of these episodes of near-global ocean stagnation, the so-called oceanic anoxic events. And there was another clue hidden in the rocks, the full implications of which are only now being teased out. Each oceanic anoxic event was linked to a super greenhouse world.
Now, we know that the whole of the Jurassic and the Cretaceous was a warm greenhouse period, but there seem to have been periods or intervals of unusual warmth within that background greenhouse, if you like, to which these events correspond in time.
What we find out is that those intervals of time are these super greenhouse climates, and they were very different worlds. They were ice-free worlds, and we seem to have good supporting evidence for high atmospheric CO2 levels as well.
If you look at these times, these oceanic anoxic events, they seem to correlate with intervals of excess volcanism. And these huge outpourings of lava would have vented sulfur dioxide and carbon dioxide, and of course the latter would have promoted global warming.
The lead up to every super greenhouse and matching oceanic anoxic event was the same. So the critical question for us becomes, how much carbon dioxide does it take to trigger such dramatic changes? That answer can be found in the ancient plants and their descendants still found growing today, like the amazing ginkgo.
Here we have a ginkgo plant. These essentially evolved about 200 million years ago, and we can see they have a very distinctive leaf shape. And essentially these probably formed a major component of the diet of dinosaurs through the Cretaceous and Jurassic. If you compare one of these modern leaves with a fossil ginkgo leaf, they're almost identically the same. And so by looking at the structure of this leaf and the chemistry of it and the fossil leaves, we can actually more accurately reconstruct the environment and climate at that time.
Living ginkgo plants can be grown under both modern and prehistoric conditions. Like all plants, they take in CO2 through microscopic pores in their leaves. The more carbon dioxide in the air, the fewer pores the leaves need.
Thank you, Holly.
Comparing pore numbers between living and fossil leaves gives a measure of how much CO2 was swirling through the ancient forests.
We find out, based on these plant fossils, that CO2 levels were about 4 to 5 times greater than they are today.
Four or 5 times more CO2 than our pre-industrial levels gave you seas so warm you could swim at the South Pole. But don't think of the planet during a super greenhouse as one big tropical paradise. This was a world dangerously out of kilter. As temperatures go up, so does the rate of evaporation and the humidity. The obvious result was more rain, falling heavily in powerful tropical storms. The rain, when it came, would have been more acidic than today, burning vegetation and etching into the rocks and soils. This probably explains the sudden flood of plant food into the ocean.
So huge amount of warming, huge amount of evaporation, lots of clouds, lots of rainfall, swollen rivers wending their way down into the ocean, bringing sediment, but also bringing nutrients like nitrate and phosphate, the sort of things you'd pour on your pot plant to make it grow in a more sort of spectacular way. These also fertilize the oceans, and they encourage the plankton, and they encourage particular types of plankton, particularly organic wall plankton and bacteria that go to make up our black shales that become our potential petroleum source rocks.
Such a flood of nutrients and the plankton blooms it triggered might have been enough to begin an anoxic event on its own.